Hi, I'm Yasuto Watanabe from the University of Tokyo. I talk about the competition between continental and seafloor weathering on Earth-like planets. Detecting the extraterrestrial life is one of the ultimate goals of the observations of exoplanets. Upcoming observations of exoplanetary atmosphere would allow us to detect the sign of life in the future so that the process controlling the composition of the planetary atmosphere is now actively discussed. Among the constituents of the planetary atmosphere, oxygen has been discussed to be one of the strong biosignatures if detected on exoplanet. In the present atmosphere of the Earth, oxygen comprises 21%. Because oxygen is produced by oxygenic photosynthesis, high concentration of oxygen in the exoplanetary atmosphere may indicate the existence of life. Thus, how the oxygen level is controlled in the planetary atmosphere is crucial to interpret the biosignature. For this purpose, we focus on the evolution of the oxygen level on Earth. In the history of the Earth, the atmospheric oxygen level was not kept as high as it is today. In the early years, the oxygen level was smaller than the present by more than 6 orders of magnitude. From such an anoxic condition, the atmospheric oxygen level abruptly increased at around 2.3 billion years ago, which is known as the Great Oxidation Event. Various mechanisms have been proposed to explain the Great Oxidation Event, but here I focus on the mechanism to produce the oxygen on the Earth. In the present ocean, the production rate of oxygen is limited by the supply of nutrient. On a global perspective, the marine primary productivity is limited by the riverine input of phosphorus. Thus, the atmospheric oxygen level is strongly linked to the phosphorus cycle on the planetary surface. Phosphorus is produced during the weathering of the carbonate and silicate mineral on the continental crust and is removed from the ocean as an organic carbon or inorganic compounds. Weathering of seafloor basalt is not expected to provide phosphorus because it precipitates as an apatite in the seafloor, so the phosphorus input rate and the atmospheric oxygen level depends on the continental weathering efficiency. So the red shaded area in the right figure is the marine primary productivity estimated based on the phosphorus budget, which is increased during the middle to late Archean. This increase is driven by the growth of the continental crust, which is estimated to have happened during this period. Thus, the growth of the continental crust would become crucial in controlling the atmospheric composition through the biogeochemical processes associated with the phosphorus cycle. However, the consequence of the continental growth on the atmospheric composition has not been systematically demonstrated. And one of the other important aspects of the Earth-like planets is the variation of orbital parameters. These are the calculated variations of obliquity and the planetary orbital eccentricity of the past Earth and Mars. It is well known that this kind of orbital variation have caused the glacial cycle on quaternary Earth, even though the change in the orbital parameters on Earth, especially obliquity, is small because of the existence of the Moon. In a broader context of the exoplanet, the values of orbital parameters could vary in a wider range of the parameter space. It has been discussed that the different values of obliquity and eccentricity could affect the climate and habitability of Earth-like planets. However, how the different values of orbital parameters could affect the coupled system of climate, biosphere, and atmosphere has not been systematically demonstrated. So, our purpose here is to elucidate the links between the growth of the continental crust, orbital parameters, and the atmospheric composition to discuss the condition to achieve the high atmospheric oxygen level in the atmosphere of the Earth and Earth-like planets with phosphorus-limited marine biosphere. For this purpose, we employed a simplified ocean and atmosphere box model in which a long-term steady state of phosphorus, carbon, and oxygen cycle is calculated. We used the parameterization of atmosphere photochemistry to calculate the budget of oxygen in the atmosphere. For the climate model, we used the parameterization based on one-dimensional radiative convective models, and we also used the meridional one-dimensional energy-balanced climate model to elucidate the roles of orbital parameters. The steady-state CO2 level is buffered by the continental and seafloor weathering, whose relative contribution becomes crucial on the phosphorus cycle. So first, we show the dependencies of the congenital weathering and seafloor weathering on CO2 and temperature, which becomes crucial in controlling the riverine phosphorus input rate. In this figure, the sensitivity of continent and seafloor weathering to the atmospheric CO2 level and temperature is shown. The continental weathering has a stronger CO2 dependency, while seafloor weathering has a much stronger temperature dependency. As a result, combining these dependencies, seafloor weathering rate has a stronger sensitivity to the climate warming caused by the change in atmospheric CO2 level, while the continental weathering rate also increases with the CO2-driven warming. As a result, the riverine phosphorus input rate is also increased because continental weathering is enhanced with the CO2-driven climate warming. Because not only the continental weathering but also the seafloor weathering buffers the climate, the phosphorus input rate depends on the climate change, as shown in this schematic. So next we discuss the sensitivity to the methane-driven warming. In this figure, the response of the phosphorus supply rate to the atmospheric methane level is summarized. Different lines represent the result with different CO2 outgassing flux. Because methane is a strong greenhouse gas, it increases the equilibrium surface temperature, while it decreases the equilibrium atmospheric CO2 level through a silicate weathering negative feedback. Because lower atmospheric CO2 level and higher surface temperature promotes the seafloor weathering strongly, the increase in the atmospheric methane level leads to the decrease in the continental weathering, as shown in the solid line. Hence, the riverine phosphorus supply rate is also decreased, like this. Thus, the competition between continental and seafloor weathering could affect the phosphorus input rate in the ocean. Then what happens if continent area is increased as a result of the continental growth? These are the response of the CO2, phosphorus input rate, and oxygen level against the increase in continental area. Different lines represent a different CO2 outgassing rate. As the continental area increases, steady-state CO2 level is decreased as a result of an increasing continental weathering efficiency. The primary productivity in the ocean increases as a result of an increased phosphorus input to the ocean. So now we see the atmospheric oxygen level. When the content area is very small, there's only an equilibrium with small atmospheric oxygen level, even with large CO2 outgassing rate. With the present CO2 outgassing rate shown in blue line, the atmospheric oxygen level slightly increases, but it is still kept low even with the present content area. On the other hand, when the CO2 outgassing rate is sufficient, the branch of low oxygen level disappears as the continent area increases as the gray line, and the abrupt rise of oxygen is triggered. So, continental growth can drive the abrupt increase in the atmospheric oxygen when the CO2 outgassing rate is sufficient. Next, we see the dependency of our model on orbital parameters. This is a response of the CO2 and global annual mean temperature, surface temperature, and the weathering rates to the different values of mean eccentricity of a planet. The atmospheric CO2 level decreases and the surface temperature increases against the increasing eccentricity. In this case, the solar irradiance at low latitude regions increases with the increasing eccentricity, so that the global mean surface temperature also increases. Because continental weathering is less effective under low CO2 and high temperature conditions, their phosphorus input and the marine primary productivity are small and a high eccentricity. On the other hand, this is a response of the different mean obliquity of a planet. The atmospheric CO2 level is peaked at around 40 to 50 degrees of obliquity, so that the weathering rate is also dependent on obliquity. This is associated with the latitudinal distribution of the insulation forcing. It is uniformly distributed at around these values of obliquity, which resulted in the low global temperature. Thus, both obliquity and eccentricity could affect the marine biosphere and atmosphere through the competition of the continental and seafloor weathering. So here we summarize the response of the CO2 primary productivity and the atmospheric oxygen level to the different values of obliquity and eccentricity. As we showed, the atmospheric CO2 level and the primary productivity is high under the condition with low eccentricity and also dependent on obliquity. As a result, the range of the condition that can sustain the high atmospheric oxygen level could vary as in the case we are showing here. Thus, orbital parameters are important not only for climate and habitability, but also the atmosphere and marine biogeochemistry through the competition between continental and seafloor weathering. So, this is a summary of our presentation. The marine biosphere and atmospheric composition could be affected by the CO2 and methane-driven warmings, and also by continental growth, and also by the different values of orbital parameters through the competition between continental and seafloor weathering, which is a fundamental process for the Earth-like planets with land and ocean. Thank you very much.